Okay, in this video, we are going to look at the algebraic properties of regular expressions. There are some properties, there are some closure properties, and then there are some properties like associativity, commutativity, etc., which are very similar to the Boolean algebra rules. But in a sense, there are some key differences compared to the Boolean algebra rules. So we'll see one by one.
Now let us look at the algebraic properties one by one. So the first property that we refer here is the closure property. So inside closure property, we have got three items. One is claim closure, union, and concatenation. Okay, so the claim closure tells you that if R1 is a regular expression, then R1 star is also a regular expression. Similarly, the union tells you that if R1 and R2 are regular expressions, then R1 plus R2 is also a regular expression. And in the very same way, concatenation property tells you that if R1 and R2 are regular expressions, R1 dot R2 is also a regular expression. Now, to prove them is very simple. So we are already aware that R1, it's already given that R1 and R2 are regular expressions. Okay, so it means that we can represent R1 and R2 using a finite automata. So suppose if you want to prove that R1 star is also a regular expression, what we need to prove is that R1 star can also be represented using a finite automata. So what we want to prove R1 star is a regular expression is that R1 star can be represented using a finite automata. So if we are able to prove that R1 star can be represented using a finite automata, it becomes very clear that R1 star can also be represented using a regular expression. So that's why R1 star is also a regular expression. So proving that is not very difficult. So let's do that. Now let us draw a finite automata which represents a language which is represented by R1. Okay, so let's assume that QR1 is the starting state of that language. Okay, QR1 is the starting state. QR1 and FR1 is the final state of that particular language. So let's say QR1 and FR1. So I'm double circling FR1 to indicate that it's the final state. So I'm not bothered about the internal details of that particular regular expression, particular language. There can be intermediate states and transitions in between. So I'm not bothered about this. So as long as what I know here is that this is the starting state and this is the final state. Okay, so this actually represents a language L1. This is a finite automation for representing a language L1, which can be equivalently represented by the regular expression, say R1. So the finite automata that you see here actually represents the language L1, which can be represented by the regular expression R1. And we know that R1 is this is a proper finite automation. Okay. Now to convert this into R1 star. Okay, so what we essentially need is that. What I'm going to do now here is that I'm going to add some states. Okay, so I'm going to add a Q0 here, which is my new starting state, and upon getting an epsilon, I will be going to QR. Okay, and also I'm going to add a new final state, say F. So my old final state is no longer my final state now. Okay, so I'm going to delete the double circle to indicate that this is no longer my final state. Okay, so my final state now is F. Okay, so I'm just deleting the double circle. Okay, so I have added two different states, one to represent the new starting state, the other one to represent the new final state. Okay, now as you may be aware that R1 star also has to accept an empty string, right? So if you look at this particular diagram over here, it is not very trivial that if you just give an epsilon, whether it will accept it or not. Okay, there should be an epsilon transition. There should be an epsilon transition from the starting state to the ending state to represent the cell, right? So what we can essentially do is we can have a transition from the starting state to the ending state upon getting an epsilon. So this will make sure that if you are getting an epsilon, because our epsilon is a part of R1 star, and if you are just getting an epsilon in your input string, it will also be getting accepted. Now we want to say, now let's say my R1 is a string AB. Now we are very sure that the automata that we started with, that is this particular automata, is capable of accepting R1, that is any string. Okay, so the string, if the string contains a pattern, if the string is AB, it will surely accept that. Okay, so that's how it was designed. Now, if I want to make it accept any number of patterns of AB, suppose I want to accept AB, 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 all these. Okay, so that it is going to accept all the strings which are there in R1 star. So to do so, what we want to do here is that if you are at FR1, it means that you have seen an AB. Now, to make it accept multiple ABs, we should also have a transition from FR1 back to QR1 on just seeing an epsilon. Okay. So here you have a provision. Now, in this DFA, in this finite automata, if you are given with AB, AB, so upon seeing the first AB itself, you will be here. Okay, you'll be here at FR1. And for the next AB, you can take this path along epsilon, and then when you see the next AB pattern, then again you will be in FR1. Okay, so any number of patterns of AB, you have the option of coming back to the final state. And from this FR1, upon getting an epsilon, you can get to the final state. And an epsilon, you don't have to do anything. If so AB is nothing but AB epsilon. That's clear. So that there are always, so if you look at this particular finite automata that we have drawn, so this is capable of accepting epsilon string and any number of patterns of the regular expression R1. Okay, so again, this diagram that you see here is also a finite automata. So this is an epsilon NFA. But remember, given an epsilon NFA, we can convert it into any type of FA. We can convert it into an NFA, and once you have an NFA, you can convert it into a DFA and so on. Okay, so so since we can draw this diagram, we can derive this diagram from R1 itself, from the diagram of R1 itself. So what we have done here is we have drawn the diagram of R1, that is a finite automata of R1, and we could easily extend it without without having any conflict with the definition of a finite automata. We could actually extend it to a new finite automata which can accept R1 star. Okay, so since I am able to design a finite automata for R1 star, it is the proof that R1 star is also regular. Okay, so if R1 is regular, this proves that R1 star is also regular. So in the same way, in the very same way, you can prove for R1 plus R2 and R1 dot R2. Remember, when we have seen the previous video regarding the union and concatenation of languages, we looked at how we can prove if L1 and L2 are given. If L1 and L2 are given as regular languages, we proved that L1 plus L2 is also regular. Similarly, L1, L2 is regular. So, the very same procedure can be applied to regular expressions also. So, just assume that L1 is represented by R1 and L2 is represented by R2. And the diagram remains the same. The diagram that you've seen in the previous video is essentially applicable in this case also. So the only thing that if you're asked to prove this is to show that you'll be able to draw a finite automata for R1 plus R2 and for R1 dot R2. And that's very trivial. Okay, that's how we prove all these closure property. So we can prove plain closure, which we have already proved. In a very same manner, we can also prove the union, closure, and the concatenation, closure and concatenation. Okay. Now, the next property is the associativity property. So it states that if R1, R2, and R3 are regular expressions, then R1 plus in brackets R2 plus R3 is equivalent to in brackets R1 plus R2 plus R3. Okay, similarly, R1 concatenated with in brackets R2 R3 is going to be in brackets R1 R2 concatenated with R3. So this is something very similar to the Boolean algebra rules. You know, the rule of associativity in Boolean algebra. So there also we have seen a similar equality. Okay, so this is very same as the Boolean algebra rules. Now let's look at you can actually put some strings, put some regular expressions for all these. Okay, and then verify that this actually works. Okay, now for commutativity, the rule is that if R1 and R2 are regular expressions, R1 and R2 are regular expressions, then R1 plus R2 is R2 plus R1. Remember, this property of commutativity is only applicable on the union operation. Okay, it's only applicable for union operation. So this tells you that you have the choice of either taking an R1 or R2. It's same as telling you have the choice of taking an R2 or an R1. Both of them, has the same meaning. But this is a very interesting question. What about R1, R2, and R2, R1? Are they commutative? The answer is no. Just because we are looking at regular expressions as patterns of strings. Okay, so assume that R1, the regular expression for R1 is AB, and the regular expression for R2 is, say, BB. Okay, now when I say R1 dot R2, the equivalent regular expression will become AB followed by BB. But whereas R2 dot R1 is going to be BB dot AB. And you can see that these are entirely different. So if you see these regular expressions, which is formed by making a concatenation of R1, R2, it is completely different from the regular expression that we got by concatenating R2 with R1. So this is very, very, very important. And the property of commutativity cannot be applied to the concatenation operator or the dot operator. Okay, so the property of commutativity here in regular expressions is only valid for the union operation. That's a very important point that you have to note. In Boolean algebra, this is not so. The concatenation as well as the dot operator and the plus operator in Boolean algebra is commutative. But here it's not so. That's a very important point that you have to take note of. Now, similarly, we can also look at the distributive property. Now, before actually looking at the distributive property, I just want to emphasize the order of priority of operations when you look at regular expressions. So we know that in regular expressions we can have many symbols, many operators like star. We can have plus. We can have dot. Okay, we can also have brackets. Okay, now so given a regular expression, we should know how to evaluate that regular expression. And for evaluating, the priorities of operators are very important. So the priority of operators goes like this. So first you have priority for brackets. This is same as in the case of Boolean algebra also. Now the next priority is for star symbol, okay, and the next priority is for dot symbol, and then the last priority is for the union symbol. So this is how the priorities are allocated in regular expressions. So this is a very important point. And normally regular expressions will be indicated very clearly with brackets. If there are brackets, it will be indicated in the regular expression itself. But it's very essential to know the priority of the operators for a regular expression. So first thing, brackets, then followed by star, and then the dot operator followed by a plus. So this is how the priorities are allocated. Now, if you look at the distributive property, states that if R1 and R2, if R1, R2, and R3 are regular expressions, okay, if R1, R2, and R3 are regular expressions, R1 plus R2 into R3 is same as R1, R3 plus R2, R3. So this is called the right distributiveness, and the next law that you see here is called the left distributiveness. Note that the expression which is executed first here is going to be R1 plus, in the first case, in the first expression, this R1 plus R2 is going to be executed first. Similarly, in the second expression, R2 plus R3 is going to be executed first. That's why the first expression is called right distributive, and the second expression is called left distributive. This will the law of distributive property will work only if you are considering union first, and then concatenation. Union first, and then consider concatenation. So if you refer to the Boolean algebra, in Boolean algebra you have got two more laws, two more distributive laws, where you have concatenation first and then union later. So those two laws will not work here, just because this is a regular expression. We are dealing with regular expressions. Okay, so this is a very important point that you need to understand. Now, you should also be aware of this. So if I'm given with a regular expression, say R3, R1 plus R2, R3, okay, and upon simplification, can I do this? So if I do this like this, I'm taking R3 common and then saying R1, okay, plus R2. Now, if this is the regular expression given, can I write it like this? Is it equivalent to is it equivalent to the expression represented in 1? Now, the answer will be no. This is because if we expand this expression, what we are going to get here is going to be something like this. So you'll be getting R3, R1, getting R3, R1, because R3 concatenated with R1 plus R3 concatenated with R2. So this is what you're going to get. Now, if you look at the initial expression that we had here, it was R3, R1 plus R2, R3. You can see this term is R2, R3, whereas this term here is R3, R2. And we have already told that commutativity cannot be applied to the dot operation. So remember, R2, R3 is completely different from R3, R2. For example, if you consider R2, consider R2 as say AB, and R3 as say BB. Okay, so when I say R2, R3, R3, okay, so when I say R2, R3, it means that AB concatenated with BB. Okay, so AB is a regular expression, similarly BB is also a regular expression. And then R2, R3 would mean AB, BB, whereas R3, R2 will be different. It will be BB, AB. So, and that is the reason why we say that commutativity cannot be applied to the dot operation. Okay, so the idea here is that you cannot, if you look at this entire expression, that is R3, R1 plus R2, R3, you don't commit the mistake of taking R3 common and then putting it like this. Okay, this is going to be wrong. You cannot take R3 common from the expression that's shown in 1. Okay, so I just wanted to make this point very clear to you.